In this example, taken from Oppenheim's Signals and Systems textbook, we are given the Z transform of a signal and asked to draw its pole zero plot. In this video, however, we will go one step further. Besides drawing the pole zero diagram, we will also determine the corresponding time domain signal xn using the given ROC. Let's start by drawing the pole zero plot. The first step is to rewrite the Z transform as a rational function. To do this, we multiply both the numerator and denominator by Z. After simplification, the Z transform becomes Z minus 1/2 divided by Z plus 2. Now we have a rational Z transform where both the numerator and denominator are polynomials. As we learned earlier, the zeros of a rational Z transform are simply the roots of the numerator. Setting the numerator equal to 0 gives Z equals 1/2. Therefore, the system has 1 0 located at Z equals 1/2. Similarly, the poles are obtained by finding the roots of the denominator. Setting the denominator equal to 0 gives Z equals minus 2. Therefore, the system has one pole located at Z equals minus 2. Now let's draw the pole zero diagram. We represent the 0 with a circle at Z equals 1/2 and the pole with a cross at Z equals minus 2. The problem also specifies that the ROC satisfies the magnitude of Z is less than 2. Therefore, the ROC is the entire region inside the circle of radius 2 centered at the origin. This completes the pole zero plot. Now let's determine the corresponding time domain signal xn. We first rewrite the Z transform using partial fraction expansion. After decomposition, the expression can be written as the sum of two simpler fractions. To determine the inverse Z transform, let's briefly review two transform pairs that we introduced in previous videos. The Z transform of a to the power n un is 1 divided by 1 minus a multiplied by z to the power minus 1. With ROC, the magnitude of z greater than the magnitude of a. The Z transform of minus a to the power n multiplied by u minus n minus 1 is 1 divided by 1 minus a z to the power minus 1. With ROC, the magnitude of z less than the magnitude of a. Notice that our ROC satisfies the magnitude of z less than 2. Therefore, we must use the second transform pair. Now compare the first fraction with the standard form. From this comparison, a is equal to minus 2. Therefore, its inverse Z transform becomes minus 2 to the power n multiplied by u minus n minus 1. Now consider the second fraction. Again, a is equal to minus 2. However, this fraction also contains z to the power minus 1. Using the time-shifting property of the z transform, we know that multiplying a z transform by z to the power minus 1 corresponds to delaying the sequence by one sample. Applying this property, the inverse z transform of the second fraction becomes minus 1/2 multiplied by minus 2 to the power n minus 1 multiplied by u minus n. Finally, combining both terms, we obtain the complete time domain signal xn. Before finishing, let's point out an important observation. Since the ROC lies inside the circle, the corresponding sequence must be a left-sided sequence. This is exactly what we obtain because both unit step functions are of the form u minus n and u minus n minus 1. So the result is completely consistent with the given region of convergence. In this example, we not only draw the pole zero plot, but also found the inverse z transform by using the region of convergence and previously learned z transform pairs. If you found this tutorial helpful, please like the video, subscribe to the channel, and stay tuned for more solved examples on signals and systems. If you have any question, feel free to contact me using the email address or Telegram ID provided in the video description.